Hello and welcome to Chapter 2. We're going to take a brief look at some key facts for Chapter 2. The first thing we look at in Chapter 2 are frequency distributions or frequency tables. You've been making frequency tables all the way back since elementary school. Whenever you made a table where you kept track of you and your friends, for example, and how many times you won a certain round in games. We're obviously going to be looking at a slightly more statistically meaningful definition of a frequency table, but it's really the same idea. Basically, you're going to divide your data into separate categories or classes, and then list the number of data, or what we call the frequency, of how many are in each class. So for example, we're going to take a look here at a set of data. I've put together a group of data here about IQ scores. These are for children with low levels of lead in their blood and their resulting IQ score. We're also looking at the frequency. So for example, if you look at this class on the slide, you'll see that there were 33 children whose IQs fell between 70 and 89. Now when we look at the classes, 50 to 69, 70 to 89, 90 to 109, 110 to 129, you will notice that all of the classes are the same size. There's a consistent pattern, and that's important. A requirement of a frequency table is that there's a consistent size of class and that pattern is not disrupted. The ones that are circled are considered the lower class limits. Those are the smallest numbers that can actually belong in the class. And then, of course, 69, 89, 109, 129, 149 are your upper class limits. Those are the largest numbers that can belong in different classes. Of course, IQ scores are whole numbers. If, however, you had data that was incremental, you might have to have a class go from 50 less than or equal to X less than 70, and then the next class would start at 70. So anything below 70 would fall in the first class. Class boundaries are the numbers used to separate the classes. So for example, between the class that ends at 69 and a class that starts at 70, if you thought, for example, of like a fence between the two properties, you would put it at 69.5. It's exactly halfway in between the upper class limit of the lower class and the lower class limit of the upper class. Once you've established one of those, you'll notice that all the others are 20 apart, just like your classes themselves are 20 apart with where they start. So once you figured out one, the mathematics of it is pretty straightforward. Class midpoints are another thing we talk about when we're looking at frequency tables, and that's the value in the middle of the class. You basically add your lower class limit and your upper class limit, divide by 2. So for example, for the second class, you take 70 plus 89, you get 159. You divide by 2 and you have 79.5. That is a value that we will use later when we start to try to look and say, well, what's the average of this class? Because you don't have individual scores, you'll use the class midpoint as representative of that class. Class width is the difference between two consecutive lower class limits or two upper class limits, basically the difference between 50 and 70, 70 and 90, 90 and 110. Or if you want to look at 69 to 89, 89 to 109, 129 to 149, so forth, they're all 20 apart. The temptation is to say, well, 50 to 69 is only 19. That's the difference between the upper and lower scores. That's a range. However, that's not the class width, because if you actually counted 50, 51, 52, 53, 54, all the way up to 69, you'll notice that you have 20 numbers or 20 pieces of data. The class width is 20. Easiest way, again, is to just simply subtract 70 minus 50. Pick two of your lower or upper class limits and subtract. Why would you use a frequency distribution? Well, it's a really great way to organize and summarize a large data set. You can take a good look at the nature of the data. You can kind of see if there's patterns or gaps between certain categories. And then you have nicely organized data that will help you construct other types of graphs. If you take a look at the Chapter 2 StatCrunch video, you will see that there are a lot of different types of graphs that we can construct. We can look at a bar graph and a histogram and box plots and scatter plots if we have bivariate data, and quantile plots and all sorts of other pictures. But one of the things we need to do in order to do those kinds of graphs is to organize our data first. The steps on this slide I will leave you to read on your own. These are actually the steps you would go to if you're going to construct a frequency distribution from scratch. In our homework problems, we're actually given the framework sort of set up for us, so you don't necessarily have to figure out how many classes you're going to have or anything like that. Relative frequency basically means that you're taking the frequency in that class. For example, 33 children scored between 79 and or 70 and 99 or something like that on their IQ test, you would take that and you would divide by the total number, and it gives you a percentage. So relative to the total, you're gaining a percentage that fell in that class. So for example, 33 scored an IQ between 70 and 89. There are a total of 2 plus 33 plus 35 plus 7 plus 8 for a total of 78 children. 33 divided by 78 is 42.3%. Be careful here with rounding. You want to make sure that your percentages here are not rounded by too much, because then when you add these up, you get something dramatically different from 100%. You really don't want to do that. Cumulative frequency, of course, means you're totaling as you go. So after we did the first class, we've had 2 children. After we did the second class, we have 2 plus 33 or 35 children, 35 plus 35, now 70 children, and so forth. When you get down to the last box, this total should be your total number of data. So where does this link with other things we're going to talk about in this course? Well, the whole concept of the normal distribution. A normal distribution, or what a lot of you think of as a bell curve, is where your frequencies start kind of low, then they go high in the center, and then they decrease again to the other side. And it's basically symmetric. So if you look at a graph that had gaps, for example, then you would assume that it was not a normal distribution. The example we're going to look at here is one with randomly selected pennies. Pennies made before 1983 were 95% copper. Pennies made after 1983 were only 2.5% copper. So let's see if anything changed. So we're looking at the weights of pennies. So we have a handful of pennies we're looking at, and 37 of them weigh maybe around 2.5 grams, and 33 of them weigh around 3 to 3.2 grams. So you can suggest here pretty quickly that you're probably drawing from 2 different populations, and we know that. We're drawing from pennies made before 1983 and those made after. This would not be a normal distribution. You have a bulk of scores at one end and a bulk of scores at the other end, and in the middle there's nothing. Okay. Looking at the next section, we're going to look at histograms. Now, histograms tie in with what we were just looking at, the concept of a normal distribution. We want to use a histogram to analyze the shape of our data. So once we have a frequency chart, or once the software creates a frequency table for us, it then creates a histogram. So a graph that's a histogram is going to have bars of equal width. They're drawn right next to each other. They are touching, unlike a bar graph, unless there's gaps in the data. And the scale, the vertical scale on the left, is representing frequencies. So for example, here is the histogram for the same set of data we were just looking at with IQ scores. And you can see that it starts low, it goes high, and it comes back low. And again, notice that it's showing us the bulk is between 70 and 89, and then 90 to 99. Okay, so here's a relative frequency histogram, where it's showing you the percentages. Again, you still see the same pattern, it's just showing you percentages instead of the frequency. And we want to think about understanding what that distribution shows us. Remember, if we graph it, it should have a bell-shaped curve. It's a normal distribution. Frequency should go up high and then decrease again. It should be roughly symmetric. So if you take a look at it here, you can kind of see that curve overlaying it. Where's the center? Think about it. Where's the center? It kind of looks to be right around here, a little bit past 89.5, maybe around 91, 92. Is there a lot of variation? Well, there's scores that go down to 50 and up to 150. Are there outliers? Meaning, are there scores that are very different? And those are going to be some things that we're exploring more in Chapter 3. But here you start to get a visual of what our data looks like. Skewness is the term we use if you do not have a normal distribution and if the bulk of the scores extend more to one side or the other. Data skewed to the right, or what we call a positive skew, has a long right tail. So the bulk of the scores are on the left, and then you have a long tail to the right. Data skewed to the left, or negative skewed, has a longer left tail. So again, here we go. Normal curve. This is considered, the one in red is more of a uniform curve. They're all roughly the same amount. Here we have something that looks, kind of normal, but it's starting to sort of pull a little bit here. You're going to have a longer right tail, so that we would call it a right skewed, and here's one that's skewed left. We can also use what's called a quantile plot. If we look at a quantile plot for a normal distribution, the points are reasonably close to a straight line. And if they're not reasonably close to a straight line, or they have some sort of pattern that's not straight, then we know for sure it's not a normal distribution. So you can take a look here. Here's one where they're relatively close to the straight line. Here's one where they're not. And here's one where there almost looks to be maybe another type of pattern going on. They're kind of close to the straight line, but they're curved a little bit around this line. So we'll learn more about that in chapter 6, but that's another tool we can use to determine normality. Okay. And on our last section here, we're going to take a look at our last section. Other types of statistical graphs. The goal is to identify the suitable graph for the data set that we're working with. You want to be able to represent the key facts about the graph. Some graphs, of course, are very bad because they contain errors. They create misconception upon the people reading them. It's important to recognize bad graphs and identify how they're misleading. This is one of the key things as a takeaway from this chapter for all of us as consumers when we look at information in the newspapers or magazines or on the web as we're reading and we're watching the news. Be very cautious that you learn to ask questions and identify whether the graphs or the data that you're being shown is truly accurate or not. This is a scatter plot. This is the type of data that you, or type of graph, that you would use when you're comparing two variables. For example, this particular one is the waist circumference and arm circumference for men. And we're looking to see if there's a relationship between the two variables, which it kind of appears to be. Sort of as the waist circumference gets larger, the arm circumference gets larger. This is a time series graph. Basically, these are very helpful to show how things change over time. So, for example, a lot of times you're going to see years down here and then data up here. This could be, for example, the cost of houses as time passes. Okay, but obviously a time series graph has something to do with time, so that's pretty much your clincher where you're looking at some changing trend over time. A dot plot consists of a graph in which your data values are plotted each as points, kind of along a number line. So for example, if we look here at 91, 92, 93, 94, 95, there are a lot of those, but there's only one 111 and only one 141. You can kind of see very quickly where the bulk of your data is falling. And if there are, of course, multiple data values at one spot, they're just stacked on top of each other. So it gives you almost like that little image of like a normal curve starting to form. This is a stem and leaf plot, sometimes called a stem plot. This represents your data by separating it into two parts, usually something like tens and ones, the leftmost digit and the rightmost digit. This can be helpful when you have a lot of repetition. So for example, these were IQ scores again. I would kind of get tired of writing 70, 72, 73, 74, 75, 76, 77, 77, 77. So instead of writing the 7 over and over and over again, I just write the ones digits to the right. And if you sort of turn your head sideways and take a look at it, you can again see this normal curve starting to form. You sort of have a sideways normal distribution. Bar graphs you're probably very familiar with. These use bars of equal width to show frequencies of data. Typically, they're going to have gaps between the bars, of course, and you could even have multiple bar graphs where you're showing two or more sets of data. It's easy to take a quick visual, for example, males and females, and looking at median income as time passes. A Pareto chart is a bar graph for qualitative data. Now remember from chapter 1, qualitative meant naming data, descriptive data. So usually you're dealing with categories of some sort. This particular one is what contributes most to your happiness, so your family or your significant other or friends or your leisure or your work or, music, sports, etc. And they are generally arranged in descending order. So the value that you had as most frequent is going to be first thing on your graph to the least frequent all the way to the right. Pie charts, of course, are very familiar for students, typically easy to read. However, also one of the most abused forms of graphs. It's very easy to distort, and of course you can't tell what percentage each of these values are, so you're kind of guessing. The size of the pieces are supposed to be proportional, and yet I have seen examples in research articles in contemporary news magazines where the graph did not match the data, and it's very misleading then because we tend to not read the article, we tend to look at the picture to get the idea. Obviously here again, the blue represents that the family or partner is most likely to contribute to our happiness, but we can't tell from this graph if it's 60% or 70% or whether sports is 2% or 5%. You really have to kind of guess, and that does not make it super accurate. Let's say a frequency polygon. This is where we would have our class midpoint values, kind of plot those points for the frequency of each one and then connect it. Just a different way of representing the frequencies of classes. Or we could do percentages as well and do a relative frequency polygon. Here again, you are able to compare two sets side by side. So in this way, if you remove the bars, it's a little less distracting, and we're just looking at the red line representing low lead and the green line representing the high lead, students with high lead, amounts of lead in their blood. And OGIVE is a line graph that depicts cumulative frequencies. So by the time you get to the end, it should have, all of your data accounted for. In other words, 78 children. Here, very last one. And then at any point on the graph, you can kind of, connect the dots and determine how many are below that particular point. So of course, if I went to 109.5, I can see that 70 of my children have fallen below that point. Graphs, of course, can deceive, as we mentioned earlier. Take a look at this. Their scales are not, scales starting here at some value other than 0, so it looks like some things are distorted. You can have three-dimensional objects or, drawings that distort things, or you could double the side of one figure but not the other. So it kind of can be misleading. So for example, here's one with a dollar bill. And, initially you looked at it and you're like, oh, sure, of course, people with advanced degrees probably make more money. But the bars, the bars do not have the same width here, and it's very busy and distracting. So it's very difficult to convey the data that we're really trying to clearly say. Here again, the concept with the three-dimensional shapes, you can see it distorts our perception because remember, when you are only looking at a two-dimensional shape, if you double the length and double the width, it would be 4 times as large. But if we're looking three-dimensional, if we double the length, width, and height, that's 2 times 2 times 2, or 8 times as large. So this last box is 64 times as large as the first box, but the income's really only 4 times as much. 74 is only about, a little bit more than 4 times. And so this is very distorted in the perception. Okay, here's a graph where it's fair, it's objective, it's clearly labeled, there's no distractions, and I can clearly see how the incomes stack up. There's a gentleman who's involved with research and mapping and using pictures to convey some really key data. He's done some great books. If you're interested in more about graphics and perception of data, he's even looked at things such as Napoleon's maps from the 1800s. But look at Edward Tufte. But a couple key things that we can take away from him. For example, if we have small data sets with fewer than 20 samples, use a table. Don't even bother using a graph. Use a table because it's small enough that we can convey that information. The graph of the data should make me focus on the real data, not on design features or cute little pictures like the dollar bill distracted me, but I couldn't really focus on what the data was. Don't distort the data. Let the graph reveal the true nature. And I like his last comment. Most of the ink in the graph should be used for the data, not for design. So, consider, for example, that you were printing your graph. The color in there, of course, might help us sort out the categories, but most of the ink that should be used for printing that is to help us determine and answer questions about the data, not about some cutesy design. Hope that is helpful. Remember that there's also a Chapter 2 Stat Crunch video so that you can learn how to do those different types of graphs in Stat Crunch, so please access that video next. Good luck.